Howdy folks. With this discussion, I want to explore, theoretically, what is the maximum spin rate that a pulsar could spin at? A much better way of actually wording this question would be, at what rate is a pulsar spinning so fast that it would actually start ripping itself apart? And in order to do this, we're just going to use Newton's second law in a rotating frame and some classical mechanics. We're going to be taking some liberties in doing this, okay? We're not going to make... This isn't going to be as rigorous as you might think, but you're going to need to understand some classical mechanics. And so if you recognize this, if you recognize Newton's second law in a rotating frame, you'll be able to follow along. And even if you don't recognize this, if you understand cross products and multivariable calculus, you'll probably be able to follow along as well. So, of course, this is Newton's second law in a rotating frame. The rotating frame is denoted by these stars in the equation. And the thing that's obviously pretty important with Newton's second law in a rotating frame is that what we have is we have all our real force, all the conventional forces that we would have normally, except since we're in a rotating frame, we also have these fictitious forces that are being subtracted or in some cases added to that real force. Now, with these fictitious forces, the first fictitious force that we have is, of course, Coriolis, which is 2 times mass times angular velocity crossed with the first time derivative of our position, or our R vector here, in the rotating frame. Then we have mass crossed with angular velocity, crossed with angular velocity, crossed with position, which is the centrifugal force. And the last fictitious force that we have here is called the Euler force. And some of you might be looking at this and saying, hold on a minute, I thought there was only Coriolis and centrifugal. But no, there is also this Euler force, and I can understand the confusion a little bit because when I took classical mechanics and learned about rotating frames years ago, we used 4 different textbooks, and 2 of the 4 textbooks did not have this Euler force listed in them. They just had centrifugal and Coriolis. One of the textbooks called it the Euler force. The other textbook that had it just didn't mention what this force was called, and so throughout this video you might hear me refer to this force as like the unnamed or the no-name force, and that's just because that's how I learned it. It was like a running, I don't know if you would call it a joke, but it was just a running thing amongst my peers and the professor that taught this to me back in the day, that we would call this force either the Euler force or like the no-name or the unnamed force or something like that. So don't blame me, that's just how I learned it, and it's a habit that I've developed over the years. But the last force that we have here, the last fictitious force, is the Euler force. So we're going to now model out our pulsar, and I'm going to be using cylindrical coordinates for that. This is the kind of cylindrical coordinates that I'm going to use. We're going to use r hat, theta hat, and z hat. But yeah, this is the coordinates I'm going to use, and you might think it's kind of weird that if we're considering a pulsar or a neutron star, like a sphere, a big sphere in outer space, it might sound weird to use cylindrical coordinates, but you'll see why that this is a really good choice here in just a moment. So to model out our pulsar in cylindrical coordinates, the reason why we're doing all of that is because we're going to start filling in these fictitious forces here in Newton's second law, to use Newton's second law to figure out what that max spin rate is going to be. So the first thing that we need to establish is our R vector here. And so if we consider our pulsar, okay, if we consider our pulsar, and we consider that we go straight along the equator, right off to the edge, and we consider some small mass, like one particle of mass m, little m, right along the equator at theta equals 0, z equals 0, like, dead center, again, right at the equator of the neutron star, right at the edge, that would give us an R vector of big R, which is the radius of the pulsar, strictly in R hat, and 0 in theta hat, and 0 in z hat. Now we're going to take some liberties here, and in reality, if this pulsar started to spin so fast that it would like rip itself apart, you would expect some type of contraction, not contraction, but rather expansion. And we're just going to assume that R in this case is actually constant. The radius of the pulsar is constant in this case. And that's a perfectly reasonable simplification to make in this regard. I don't necessarily want to get into like the differential geometry we would have to take into account with regard to this thing beginning to expand, nor do I necessarily feel comfortable with that. So we're just going to take some liberties here, and we're going to say that our radius of the pulsar is in fact constant, because if it's in a stable state, it probably will be constant. Next, we need to consider angular velocity. And so to simplify this as well, what we're going to do is we are going to consider that our angular velocity is strictly in positive z hat. So by our right-hand rule, that means the pulsar is spinning counterclockwise. And we are also going to simplify things even more by saying that our angular velocity is also constant. Now, this simplification is not necessarily as easy to make because, as you can see right here, this is my own ephemeris that I've created here. You can see that the crab pulsar is spinning down, or its spin is slowing down gradually over time, very linearly in nature, and so it wouldn't necessarily be appropriate to model the crab pulsar's angular velocity as constant over time. But with plenty of other pulsars, it actually might be appropriate to consider constant angular velocity. Now, we know these things also go through glitches and lags and things like that with regard to their spin, but again, just for simplicity, we're going to say that angular velocity is constant. Perhaps in a future extension of this discussion, we could consider what would happen if we didn't consider a constant angular velocity, but we're not going to consider that right now. We're going to consider this angular velocity as constant, so our omega vector is just going to be omega in positive z hat. And so now we can use our r vector and our omega vector to fill in not just the real force here, but we're going to focus more so on these fictitious forces. We'll come back to the real force or the physical force later on. We're just going to establish our fictitious forces first. So the first fictitious force we're going to take a look at is Coriolis. And so this is Coriolis right here. I left the minus sign in from the subtraction, but 2 times mass times omega crossed with the first time derivative of our r vector in the rotating frame. But remember that our r vector is just capital R hat, which is the radius of our neutron star. It is constant, and so if we take a derivative of that, of course, we get a 0 vector. So this entire term for Coriolis is completely eliminated. It is not important, and it does not play a role in what we're doing here with this theoretical approximation for the max possible spin rate for a pulsar. So now we move on to centrifugal. With centrifugal, this is going to be obviously non-zero, which is really nice. So we actually need to compute some cross products. So first we're going to do omega crossed with r, which will give us omega r in theta hat. And then we'll cross omega with omega crossed with r, which will give us a negative omega squared r in r hat. Now we have a double minus sign in this case, so this is what our centrifugal force looks like. Mass times omega squared r strictly in r hat. And so we can slide that right into our Newton's second law in a rotating frame. We have one more fictitious force to go with, and that's the unnamed or the no-name force, and you might be able to see what's going to go on with this here. Omega is constant, at least with the way that with some of the liberties that I'm taking in doing this. And so again, this goes to 0. This no-name force will not play a role in our second law here. And again, I just want to remind everybody that this liberty that I'm taking by saying that angular velocity is constant is not necessarily true in a lot of cases. We're just doing this to kind of make things simple so that we could figure out just a rough idea of what the maximum possible spin rate for a pulsar is. So we have all the fictitious forces taken care of. The only one to come out of this with some type of contribution here to this scenario for modeling our pulsar spin is the centrifugal force. So now let's take a look at the physical forces, or the real forces right here. And to do that, let's take a look at a cross section here, and let's take a look at our particle of mass m, again, right along the equator, right at the edge of the radius of our pulsar, strictly at r hat. And this is our centrifugal force. Our centrifugal force is strictly in positive r hat, and it is m omega r. And I'm going to kind of treat this kind of like a free body diagram, if you will. I love free body diagrams. When I was a TA, I loved using free body diagrams because just conceptually it was really easy for me to get students to understand what was going on. So here we're just going to do the same type of thing. We're going to have a, kind of like pseudo free body diagram, if that's how you want to call it. So we got our centrifugal force pointing in positive r hat, and if we only have this force here, this tells us that the pulsar is ripping itself apart, okay? Or it's going to be expanding, at least. The radius of this thing is going to be expanding. Our mass of particle m will be moving in positive r hat. And obviously we don't expect that to be the case. So we need a force of equal magnitude in the opposite direction, pointing towards the center of the mass of our pulsar. And obviously, if we're considering a big ball of matter in outer space, an ultra dense one at that, obviously gravity is going to play an important role. So we'll say that this force here is gravity, but remember that this is pointing towards the center of our pulsar. The direction of this vector is actually in minus r hat, so we'll tack a minus out in front of that. So now we have pretty much everything that we need to do this approximation for the max spin of a pulsar. Okay, so with that all said, this is what our second law looks like for this scenario in our rotating frame. We've got gravity in negative r hat. We've got centrifugal in positive r hat. All of the little m masses can be divided out. And so, of course, again, we would expect these two forces to be equal and opposite to one another, meaning that the net force is 0. So what we can do is we can set these two equal to one another, and we can actually solve for our angular velocity, and that will help us figure out at what angular velocity this thing will get out of equilibrium. And so when we do that, we get that omega is equal to the square root of big G, our gravitational constant, big M, which is the mass of our neutron star or pulsar, divided by the radius of the pulsar cubed. Now we have a problem here. Our work is not done yet. The units of this is in radians per second, and I want to get a frequency. I want this to be in hertz or inverse seconds, so we need to find a way of getting rid of these radians. And we could do that pretty simply by taking omega and dividing it by 2 pi. I've set that equal to nu. Some of you might like a capital omega variable. Some of you might like a variable f. I prefer nu. That's the notation that I like. I'm the one making the video, so get mad at me. I kind of don't care. I like the nu variable. So nu is equal to omega divided by 2 pi, which is really just 1 on 2 pi times the square root of our gravitational constant times the mass of our pulsar divided by the radius of the pulsar cubed. And that, of course, gives us inverse seconds or hertz. And so this gives us a relationship for us to figure out how many times per second, or at what frequency the pulsar is spinning at, before the pulsar will start to rip itself apart because it's spinning so fast. So I've coded that whole thing up, and this is a chart of what we end up getting in here. I've thrown in some values for radius and for mass. For radius, I went between 5 kilometers all the way up to 16 kilometers. And for mass, I've gone from 1.2 solar masses all the way up to 3 solar masses. Now, I know that, generally speaking, for like a standard basic pulsar, if we're just considering that just basic and or theoretical pulsar here, most people default to about 1.4 solar masses in either like 10, 12, or like 15 kilometers. And so if we go with 1.4 solar masses and 15 kilometers, that puts us way the heck up here. And so we would actually get a really, really slow maximum spin rate at 1,181 hertz, or just approximately that. But as you can see, if we are considering pulsars of like much greater mass, and again, I know there's some debate about, can a pulsar be more than 2 solar masses? There's been papers that I've read that where they propose that a neutron star could be as large as, I shouldn't say as large, but as massive as like 3 solar masses. There's plenty of debate amongst the mass and radius relationship when it comes to neutron stars. We could do a whole discussion on equation of state and that if you really want me to. That's not the point of this video. The point of this video is that the maximum spin rate for a lot of these pulsars, at least theoretically, in these fairly in this fairly simple scenario that we've constructed for ourselves, shows us that pulsars can spin incredibly fast. Okay, they can spin really, really fast. Okay, now while I still have this chart up, and before we conclude, I just want to mention that this is an actual exercise that I ended up doing in like an actual research setting or scenario years ago. I have an older video where I talk about the time that I thought I'd found the fastest spinning millisecond pulsar. I thought I found a pulsar at 890 hertz. Turns out it was just new star dead time. But to make a very long story short, when I found that result, or when I found that measurement, I went to my advisor and she said, let's just take like the most simple case theoretically and just see if it's possible. And so I did this whole exercise before, and as it turns out, the 890 hertz frequency that I thought I found was actually quite reasonable based off of this. Now, obviously, we didn't stop there. We went a little bit further. And if we come over here to NRAO, it says right here, the fastest spinning pulsar spins 716 times per second. Yeah, that is, the fastest spinning pulsar that we know of. There's been some debate as to whether or not there's one from that spins more than that, but they say, generally they should possess enough self-gravity to spin as fast as 1,000 to 1,500 times per second before they slowly lose energy due to the release of gravitational radiation or break apart. So obviously with this exercise, we've grossly oversimplified this entire thing. There's very good reasons of why you're probably not going to see pulsars spinning up here around 8,000 hertz, because there's, again, a lot that we haven't taken into account. But at least, theoretically speaking, the 890 hertz that I thought I had found for a pulsar was actually quite reasonable. And so that's just a little tidbit that I wanted to share. If this was interesting to you, let me know in the comment section. If you want me to expand upon this and, start to model our angular velocity as non-constant, I think that would be a fun extension to do in exploring what the maximum spin frequency could be for a pulsar or a neutron star. But anyways, thank you all very, very much for watching, and I hope to see you all again next time.